NASA noticed something today with 3i Atlas. Nothing dramatic, no explosion, no sudden flare lighting up the sky. But the people who have been tracking this interstellar comet day after day saw enough to quietly update their models. That alone matters. Because with an object this strange, even a small adjustment can tell you whether it's finally settling down, or whether it's simply reorganizing itself before something new happens. 3. I-Atlas has never behaved like a normal comet. Not when it arrived, not at perihelion, and not now, as it moves away from the sun. Today's update doesn't solve the mystery, but it adds another piece to a puzzle that has already forced astronomers to rethink what an interstellar visitor can look like. Here's what actually changed. Every day, observatories feed fresh measurements into orbital models: position, brightness, coma structure, motion relative to gravity alone. Normally, as a comet moves outbound, everything becomes quieter, brightness fades smoothly, activity weakens, predictions get easier. That's not what 3i Atlas is doing. The first sign was its brightness. When today's data were compared to standard fading models, the comet was still brighter than expected. Not wildly brighter, nothing you'd notice without careful analysis, but consistently above where it should be. That alone isn't shocking. What matters is how that brightness behaves as the comet rotates. So scientists folded the brightness data over the rotation period, watching how light rises and falls as different surface regions face the sun and Earth. A few days ago, that light curve was chaotic, multiple peaks of varying height, irregular timing, no stable rhythm. That kind of pattern means many vents are competing, jets turning on and off unpredictably across the surface. Today's curve looks different. The dominant peak is still there, driven by the strongest active region, but the smaller peaks that used to appear randomly have smoothed out. Instead of scattered noise, there are now two consistent secondary rises appearing at the same rotational phases each cycle. The activity hasn't stopped, but it has organized. This is the difference between turbulence and structure, between static and a signal. The comet's internal behavior has shifted from disorder toward rhythm. Then came the coma. At first glance, nothing seems unusual. The inner glow is still present. The tail still extends away from the sun. But closer inspection tells a subtler story. Previously, the inner coma was strongly asymmetric, bright on one side, stretched and distorted as if one hemisphere was doing most of the venting. That imbalance had become one of 3i Atlas's defining features. In today's stacked images, that asymmetry has softened. The inner coma is rounder. The brightest region is less displaced. The flow of material near the nucleus appears smoother, less kinked, less turbulent. This isn't a transformation, it's a relaxation. Like a system that was wildly off balance and is now wobbling less, not stable yet, but closer. Finally, the orbital solution. Active comets don't follow gravity alone. Jets act like tiny rocket engines, pushing the nucleus in specific directions. For weeks, 3i Atlas has been difficult to model because the direction and strength of that push kept changing. Each update required large corrections. Today, that changed. The non-gravitational acceleration is still present, but its direction didn't wander, its magnitude didn't jump. When the solver refit the data, it preferred a smoother, more coherent trend extending back several days. That matters. It means the forces acting on the comet have become more predictable. Put it all together. The light curve has organized, the inner coma has rounded out, the thrust direction has stabilized. This is why NASA updated the model. So what does it mean? One interpretation is that 3I Atlas is exiting its most chaotic phase. After perihelion, multiple volatile layers were responding at once, shallow ice blowing off, deeper pockets activating late, fractures opening unpredictably under thermal stress. That kind of cascading complexity produces exactly the behavior we saw earlier. Now, deeper heating may be stabilizing. A smaller number of dominant vents may have taken over. Activity is still strong, but it's no longer competing across the entire surface. That naturally produces smoother light curves, more symmetric coma, and steadier thrust. That would be the optimistic scenario. The comet is finding a new equilibrium as it cools. But there's another possibility. Sometimes systems look calmer just before failure. If activity is concentrated into fewer regions, those regions may now be under greater stress. Instead of many small cracks sharing the load, one or two dominant fractures could be bearing most of the pressure. From the outside, everything looks tidy and stable. Internally, stress can be increasing. We've seen this before with comets that lack. We've seen this before with comets that later fragmented. Right now, there's no evidence of breakup, no multiple nuclei, no explosive outbursts, but there's also no guarantee this stability will last. That's what makes this update important. 3I Atlas hasn't gone quiet. It hasn't exploded. It is reorganized. And with an interstellar object, that's exactly the phase you want to watch most closely. This is only the third confirmed visitor from another star system. Each one has behaved differently. Oumuamua challenged our assumptions about shape and acceleration. Borisov looked more comet-like, but still unusual. 3I Atlas is now teaching us that even when something resembles a comet, it may operate under rules shaped far beyond our solar system. Every subtle change adds to that lesson. Whether this object stabilizes and fades quietly into interstellar space, or whether this calm is just a pause before another surprise, we are watching something humanity has almost never been able to watch before. An alien object learning how to survive under a foreign star. And that story is still unfolding.